Thank you very much. Thank you for the invitation. So I know I'm working for Orange Research. I'm directing a research domain on security and trust. So I would like to testify about one use case we are conducting with Quandela about cybersecurity. In fact, the issue is about malware. Malware stands for malicious software that are built to intentionally harm an information system. You can see on the graphs that AV Test, which is an independent research institute for IT security located in Germany, record every day, I say every day, around 450,000 new malware or potential unwanted applications. And they are more and more sophisticated and can be even assisted by artificial intelligence. As you can see on this graph, the accumulated number of those new malware is growing. And for us, detecting them, it's really an important issue. At the beginning, we started with machine learning on classical computers. But we realized rapidly that the model we get from those classical computers can be attacked easily. It means that I can change a little bit the executable file and it becomes harmless for the models. The second thing I said with the graph I showed before is that malware are evolving faster and faster. Okay, so we have no new data about those malware. We also face with the limited number of data because of copyright, because malware are handled by antivirus companies and so on, and don't want to share the data. We don't want to have large models because the large models means that you need to update them with energy cost, and we want to limit those costs. This motivates us to move to quantum computing because we think that quantum machine learning has some interesting properties, and we want to check if it's true or not. We are still in research. And we start with superconducting-qubit technology. Before we setting up a collaboration with Quandela, and we have a basis of comparison, and we found that we get 10% of accuracy improvement using Quandela technology. As you know, photonic technology is one of the technologies that consume the least. It means that the model we get consume the least. It was one of our objectives. So we get smaller models, and it's exactly what Jacques Charles talked before. We are using a hybrid mode, using some classical computers, but also Quandela's computers. But we separate, we rethink our algorithm to see what could be should be addressed by quantum computers and what should be done by classical computers. So for us, the more you have photon, it means that the more variable we can handle. So having this receipt is really something interesting to know. And we now want to investigate new techniques. So we will again maintain the partnership this year. We are discussing with Research, which is in the pivot, to continue investigating your technology. We are happy with that, and it appeared to us for this use case that is the most suitable technology for us.
Thank you, Adam. And first of all, I'm very happy to be here with all of you, and happy to see all these people celebrate Lucy with us. It is a great milestone of which we are very proud of. Before going back to the use case that Adam already started to present, I would like to actually spend, first of all, a few words about how actually Quandela has a full stack approach. When one thinks about Quandela, I guess the first thing that comes to mind is actually, of course, the hardware manufacturing and the processors. But we actually deal with a lot of other parts of this process. There is an entire branch dedicated to the development of the open source framework to deal with our machines and to program them, both for us internally, of course, but also for external users. We have Perceval and Merck. And after that, there is on top of that actually an entire layer dedicated to the quantum algorithms, of which I'm part of, which we have the chance to work with a lot of great partners and to have also a lot of projects internally for the development of algorithms that are designed for photonic quantum computers. Last but not least, we have also an entire branch dedicated to the access to our machines that can be done all over the world thanks to the internet. This is the part dedicated to the Quandela cloud with which we communicate with our machines, and everybody basically can send their own quantum algorithm on our machines. For those that are not yet familiar with our technology works, I want you to have it in mind before jumping back to the use case so that you know what it is when I speak about quantum layers, some quantum parts of an algorithm. Our machine works of course, in a more complicated way, but I will try to simplify it for you. The first layer that we have is the quantum source. It's a quantum dot that behaves as an artificial atom, and that, when excited by a laser, re-emits photons with a very specific wavelength and very specific characteristic. This is very important because basically those photons are indistinguishable. This means that we can use them, their quantum properties and their interference. After that, they enter a demultiplexer, which basically they are routed in different optical fibers, and then they travel into those optical fibers that have different lengths, so that can be synchronized all to arrive at the same times on to our photonic circuit. That is where actually the quantum algorithm takes life, let's say. It's with bit splitter and phase shifter then that we change the quantum state of photons so that we can obtain the answer to the question we were asked to answer to. And what you see at the end, when we do the measurements, you see a lot of ones and zero, which is the binary counterpart of the measurements that we do. We perform such experiments several times so that we can have reliable statistics of the answer at the end of our circuits, and so we can send you what is the answer to the question you asked to us. So keep that in mind for what I'm going to tell you after when I will talk about quantum. This is basically what happens behind. First of all, how did we do that? The first thing we did was to translate the malwares into images. This is a quite known technique in classical machine learning. We used the binary translation of those codes into make them into images, so that we could search for some kind of special features that could tell us whether or not the code was malicious or benign. We fed those images to our algorithm. That was a quantum convolutional neural network, which, as we said before, it's basically a new hybridization between classical and quantum. We have a quantum part, the quantum layer in which the data are encoded, and then we have a part that is still a classical convolutional neural network. So it's an hybridization between the two. After we trained the model, we were able to find families of different malwares, and so the idea, the ultimate goal for this kind of algorithm would be to help people that work in cybersecurity to find a way to protect with tailored protection with respect to this horizontal level. We presented this use case already in 2025 at Vivatech, and we are very proud and happy with the outcome we had that actually paves the way to some interesting projections for future quantum advantage. What we actually found out is that by using a quantum layer, so via this hybridization, we actually find a drastic reduction of the number of parameters needed to solve a task of a certain difficulty. What does this mean concretely? It means that we could, in principle, tackle the same size of the problem with less parameters in quantum, so more efficiently, more precisely, and also, as Adam said before, with less energy, which is something that is very important to us all at Quandela. So as you can see in the graph to the right, the orange curve shows us how the number of parameters needed for classical convolutional neural network grows with respect to the difficulty of the task, and you can see that the quantum counterpart, which is the blue one, grows more slowly than the classical one. Even though, unfortunately, we still don't have the size of the hardware to prove concretely the quantum advantage by doing the runs on the machines, these projections tell us that actually we are on the good way, on the good route toward quantum advantage. This was one of the many use cases that we had the chance to work on, and it's part of the larger field of hybrid quantum AI that we strongly believe is one of the most promising fields to find quantum advantage quickly. We worked in finance with the Crédit Agricole, in chemistry, with total energy, and also in a generative of images from day to night with BMW and Airbus. I won't continue with the big list that we have behind, but trust me, we have a lot of use cases. And also outside of AI, we still work with other partners in energy, in pharmaceutical, and also in other aspects of cybersecurity with the generation of certified random numbers with OVH Cloud. Before concluding this presentation, I would like actually to show you a video that shows you an example of use case very similar to the one of malware detection, because it's still about the image recognition, but from a different point of view. Another kind of promising algorithm is the quantum reservoir computing, and specifically this is an algorithm called quantum optical reservoir computing, in which, as you can imagine, photons are used to perform the image recognition. So what we see in here is a real image of taken from Google Maps of our airport, which we see how with the photonic reservoir computing we can recognize different categories of objects in the image. You can see the square, the red square that discovers the image to the left bit by bit, and as soon as more than half of the object, or roughly half of the object is shown, the model has no doubt anymore and is able to recognize what object we are actually seeking. This was it for my presentation. I hope that you enjoyed, and thanks again for being here. And if you have any questions, even though we don't have the time, don't hesitate to reach me by email.
Thank you.
Thank you very much. Thank you like that.
Say the I'm not sure.